Speaker is Gianluca. Gianluca Filippa, you need to install your presentation. He's a researcher at a regional agency for the protection of the environment in Valle d'Aosta in Italy. And his work focuses mostly on impact of climate change on mountain ecosystems. And he's going to show us something of how you can assess phenology using remote sensing and other sensors. He's researching also snow and water, for example, snow water equivalent measurement and modeling. And he's also very interested in climate data, climate change scenarios, and indices of climate change impacts.
Thank you very much. Okay, so I'm the one that is separating you from the next coffee break, so I will try to be as fast and painless as possible. I want to first of all thank Sandra for the great opportunity to be here and present my work. And as part of a regional environmental agency, we are in charge of the monitoring of the environment. We also do some research, but this research is really focused on management tools. So what I will present today is actually a set of satellite-derived products that are used by the local government as management tools for grasslands. A few words as a background. So grasslands provide very important ecosystem services in terms of biodiversity. They are a reservoir of biodiversity, water regulation and soil protection, and this is also the case for mountain grasslands as well. They also have a very high economic importance in terms of livestock farming, of high quality dairy products and tourism. Think, for example, that in Aosta Valley, which is the place I work, 90% of the agricultural products are derived from grasslands and pastures and meadows. And they also represent a cultural heritage because, as we know, the grasslands are shaping the mountain landscape since millennia, and so they also are very important in terms of cultural heritage. So the challenge here is that we need sustainable management tools and the information that we have to get to in order to maintain the management of the grasslands that must be accurate and timely. The monitoring of mountain grassland is quite a challenging task because we have a huge problem of accessibility. Rugged terrain makes a field survey very difficult, time-consuming and also costly. We have a huge spatial heterogeneity, sharp changes in altitude, in aspect and soil, which led to very diverse vegetation, but as we will see, it also brings together a particular challenge in terms of remote sensing. On top of that, we also have, of course, climate change, which is determining shift in phenology, in species distribution, and also in water availability. Another important issue is land abandonment. Probably is in our case is even more important than climate change, or at least the combination of both led to dramatic changes. And so land abandonment is also an important issue. So in summary, we have the need for efficient and non-invasive methods for monitoring vast and complex area. And remote sensing comes at help in that because it is a powerful tool for spatial temporal monitoring. And apart from the fancy definition that you find in the first row, I think that the most important thing here is that the advantages of using remote sensing is that we can cover wide areas. The observations that we get are repeated over time. And this is a kind of a very objective data collection. And it's also a cost-effective method for large areas. So it is ideal for monitoring dynamics of mountain grassland even on a regional perspective. So now let me make a point on time resolution. What we see here is a time series of 1 year of development of vegetation on a grassland site. This is made by webcam sensor that are no more than digital cameras that take the same picture of the same scene over time. We have daily photograms, even more than daily, but for the purpose of this illustration, daily is enough. And as you can see here, we have a baseline during the winter, then we have a sudden increase in April or May. This is a very fast increase because in 1 month we reach the maximum of the seasonal development that you can see here. Afterwards, what we get here is a grass cut, and we see the drop, the effect on the green index that we use here. We normally use NDVI, but the story is about the same. So it's just a vegetation index that represents the seasonal dynamics. And then after just a few days, we see the sudden increase of the signal and up to an almost complete recovery after like 5 or 6 days. So if we have to monitor this process with a less resoluted in time sensor, like for example MODIS, which is the sensor that has been used historically for monitoring vegetation dynamics and phenology, we keep seeing the signal, but the amplitude is much less. Also the signal is much more smoothed. We cannot really distinguish how the recovery phenomenon goes on. And if we move to monthly time scale, as for Landsat, for example, we hardly see anything related to this clear cut. So this means that temporal resolution is really a key feature when we want to detect a fast process such as vegetation development. Landsat satellites, they have a 30-meter spatial resolution. MODIS has 250-meter spatial resolution, so I'm talking about a trade-off between temporal and spatial resolution, which is the key feature when we talk about satellite data to monitor grasslands. So now let me make a point on space resolution. This is let's say a landscape of low mountains. It's actually close to my place. And as you can see here, in a few kilometers, we have a very diverse landscape with a very fragmented feature. We have orchards, we have vineyards, we have grasslands, we have some forests here, we have the river and some urban areas. So if we are to describe this landscape with the MODIS data that we had until 2016, the resolution is 250 meters. Each of these square would represent a pixel. So this means that the information that we have here is an average of at least, I don't know, 6 or 7 plant functional types, different plant functional types. So no way to describe in detail what happens on this surface. Nowadays, we have this opportunity, which is the spatial resolution of the new is not new anymore, but anyway, after 2016, the Sentinel-2 family of satellites started providing data at 10 meters spatial resolution. So this is the spatial resolution, the spatial detail that is required to describe an heterogeneous system such as the mountain Alps. So the point is that we have to find the best trade-off between spatial and temporal resolution, and Sentinel-2 data is a really it has represented really a Copernican revolution on this topic. So to summarize, we have a 10-meter spatial resolution, which is ideal for agricultural mapping. We have 5 days revisiting time, which is a sufficient time resolution to capture the fast vegetational signal. We have 13 spectral bands, which means the calculation of many indices, and also a base for machine learning training, for an effective machine learning training. Most importantly, it is an archive of free and open access images, and is also highly supported in the sense that Copernicus, which is providing those data, also has provided a number of high resolution layers that we will talk about later. Anyway, cloud cover is a major issue in mountains, and this is an issue that we also have, that we always have to take into account. But the problem is that out of the self-Copernicus product, as the one that I was mentioning before, they are not tuned for a mountain landscape. So they often misrepresent the complex topography of the Alps. So that's why there is the need of tailored satellite data, and that's what we did with a 10 years cooperation with local agricultural department, during which we addressed a number of different topics. And now for this talk I will concentrate on these three. The first one is resource assessment in terms of grassland extent and productivity. The second one has to do with regulation and management, so how to detect the actual usage of the surfaces. And then a final part on early warnings, which is the development of quasi-real-time tools for the monitoring of the extreme events. The rationale behind this process and the 10-year cooperation is the co-construction. So we have been putting a lot of effort in the dialogue with the local authority in order to really tailor those products for their needs. A very rapid geographical context. Aosta Valley is a 3,200 square kilometers inner Alpine valley, so it has continental climate. We are 100% mountains, so the elevation ranges between 300 and 4,800 meters. We have steep temperature gradients, and we also have quite a huge precipitation gradient from 500 millimeters here, which is the yearly precipitation in Jerusalem, just has a benchmark, and up to 4 times more in the mountain ridges here. And still 40–50% of this falls as snow, so snow is an important component of water cycle here. So the first theme is, the first topic is resource assessment. We determine the grassland area by means of a supervised machine learning algorithm. But we reached 90% of accuracy in grassland detection. And second, we determine the productivity of these grassland areas. This was coupled in situ biomass, destructive biomass measurement that we have access to on a huge database, a regional database, historical one, coupled with remote sensing by means of regression models, and so we determine productivity. Here is how it looks like at the regional level. So we have a productivity ranging from 0.3 to about 15 tons per hectare. The majority of the more productive grasslands are in the Central Valley, which is where the meadows are. Then when we move upwards, we see this nice gradient of decreasing productivity. We have about 900 square kilometers of grasslands, of which about 600 square kilometers are effectively used as pastures and meadows. So now let's zoom to a case study at a smaller scale. We focus on this low mountain area. The range here is between 1,000 and 2,000 meters. Here we are the lowlands, relatively lowlands at 1,000 meters, where we have meadows, cut meadows. And the higher we go, the more we get pastures or mixed management, like one cut and one grazing. As you see here, there is a road here, so it's not the highest pasture that we have in the Aosta Valley, but it's some in between. It's interesting because we can show different things from this picture. So one of the first derived product from the biomass is the potential livestock rate. It's a simple model, a linear model of livestock rate from biomass with some adjustment for slope and elevation. So what we can do here is really map continuously in space the potential stocking rate. If we aggregate this information on the agricultural parcel level, this can become a true management tool for these grasslands, for the farmers. So second, passing to the regulation topic, which has to do with the utilization of the surfaces. As you know, common agricultural policy gives subsidies based on farmers' declaration on how much surface are actually in use in terms of managed grasslands and pastures. This is crossed with information at the national, at the EU level, that is used basically to check if the farmer's declaration is right or not. And this is based again on European level products. One of them is Sen4Cap, which is an initiative that is using Sentinel-2 data to determine the usage of the surfaces. But again, as I was telling you earlier, these products are really trained on a landscape that is completely different from the mountain landscape. So it hardly says anything meaningful for the mountains. So that's why we developed our own product. So we developed an algorithm for pixel by pixel detection of utilization. So to determine whether a grassland was utilized or not. And as you can see here, the process is quite simple. We take a time series of 1 year of NDVI for a given pixel. This is a typical grassland behavior. And as you can see, just as we saw before, we have the winter baseline, then we have the development. And here we have two cuts. One is here and the other one is here. So with the algorithm, we detect the drop. And we can so determine the number of utilization and also the day of the year of the utilization. The approach is pretty simple, but we have to take it with caution because, for example, this point here is not a drop due to a utilization, but is likely a misclassification of clouds. So there is a number of issues that you have to take into account with this model to be working. So this is the same landscape as we saw before, but with the map of utilized and non-utilized surfaces. As you can see, there is a good spatial consistency between the classification. There is some salt and pepper effect that we have to take into account. But anyway, this again becomes a very important tool because if we aggregate this information at the parcel level, we can say how much of the parcel is being actually used. So this product can be used as a tool to check farmers' declaration. I use the word can because the process of making this tool becoming a real effective tool has to pass through politics, and so it's not so easy to implement it in an effective way. Anyway, we are on this way. At the regional level, about 60% of the grassland surfaces are grazed or cut, according to our tool. As I mentioned before, it's a yearly product, so year by year we can update this information, and so we can provide a more detailed classification compared to the one that is run at the national level. Same figure, but with the utilization, the number of utilization. So typically in our region we have up to 3 utilization in the lowlands, but normally in this kind of landscape we have 1 or 2 utilization. And one effort that we have put is to try to validate this kind of information. Of course, the ground truth data is always lacking in this kind of study, but fortunately we have webcams. We have again the phenocams that are looking at some hotspot of vegetation that we are interested in. From webcam, and as I mentioned before, we can extract temporal signal, a temporal behavior, but at the same time we can use them as pictures and so detect by visual inspection the date of actual cut. For example, this grassland was cut 3 times. We compare, we extract the time series of Sentinel-2 and DVI, and we actually check that there is a clear drop when the cut is done, and we can check how good is the agreement between webcam defined cut, so the ground truth, and the red line, which is our algorithm. This, of course, is one of the best cases. It is not always like that, but the principle is this one. Apart from the limited number of webcam that we have installed for vegetation survey, we can take advantage also of a number of touristic webcams that are normally in place in different parts of the valley. We selected a subset of them that are actually looking at a scene where we also have grasslands and where they are close enough to detect by visual inspection the usage. And so we have 12 touristic webcams per 9 years of data, which is not too much, but at the same time not too bad as validation ground truth for our models. Last part is the evaluation of extreme events. As we all know, extreme events are not extreme anymore, but are becoming, unfortunately, everyday business. After 2022, which was a really striking year in terms of aridity and drought, even in our valley, we have started developing a specific tool for the early detection. And for example, here we have developed this kind of representation, which is an anomaly map. So current year versus average year of another product that we release yearly, which is the foliar water content. For example, this is the case of July, and as you can see, July 2002 was almost all in a negative anomaly. Also here we can evaluate it at the regional level, or we can focus on specific areas. And so that's the advantage of having a wall-to-wall representation. Another way of looking at it is another parameter is the leaf area index. It's the same anomaly for July 2022. And we can also separate this information according to, for example, elevation belt. And as you can see here, for example, we see that there was an impact at all elevation belt, but the impact was kind of stronger below 1,000 meter. If we compare to the long-term average, 2022 was much lower in the belt under 1,000 meter, which is actually the mountain belt where we have irrigation on pastures and grasslands. And so these grasslands were not irrigated. It's time to go. So, for example, this information altogether provided the basis for a derogation order, which permitted the withdrawal of livestock earlier than usual for 2022. So that means that this tool really became an operational tool at the regional level. So to conclude, remote sensing is an indispensable tool for understanding and managing mountain grassland, but for mountain, it really works only if tailored and co-constructed products are built. It represents an updatable and scalable tool for the quantification of resources. Also a support for local regulation on CAP, but that must pass through a careful negotiation. And finally, it is a quasi-real-time support for decision-making in case of extreme meteorological condition. With that, I thank you, and I welcome questions. Thanks.